This podcast was produced by OAR FM Dunedin with support from New Zealand On Air.
Whoa! Whatever happened to the ozone hole? Welcome to the OI podcast, the Otago Institute podcast. No mai, haere mai, and welcome to episode 119, Ozone, with Drs Mallika Suresh and Hannah Kessenick. I'm Dr Barb, a quantitative ecologist with a background in modelling, climate change, biodiversity conservation prioritisation, SciComm, and a PhD in botany from Otago, Whakaihu Waka, the University of Otago.
And kia ora, I'm Trudi, and I'm a jack of all trades and master of none, but most of my interests lie in the social services field, economics, history, psychology, sociology, all that kind of stuff, which is soft science. But anyway, so thank you very much for joining us for another episode of the OI podcast, the podcast for discerning listeners and discerning guests, brought to you by the Otago Institute, the Otago branch of the Royal Society for Arts and Sciences. We hope you enjoy our mix of conversation with experts from the worlds of arts, sciences and Mātauranga Māori.
And today in the studio, we are talking about the ozone hole, everything about the ozone hole. And
Do you ever wanted to know in 50 minutes?
Well, what amazes me is that we used to talk about it all the time. When I was a kid, we were talking about nothing but the ozone hole. We were talking about the ozone hole, It was just like, it was the biggest thing that was, like, it was before climate change. Like, anyone who's talking about climate change now and they're like, oh, that's terrible, or politics or general, like, end of the world. Like, when I was a kid, which granted was a few years ago now, it was all about the ozone hole. And then it sort of stopped. And
but it drove a lot of activity, especially in facilities, because we had to change a whole lot of HVAC, for the refrigerant.
What's HVAC?
Heating, cooling systems.
Oh, right.
HVAC,
Well, to me, it all seemed like it was all about refrigerants. And then like, it was
gone.
like as if they, like, found the answer and fixed it and everyone sort of outlawed the thing that was bad. And then we just had to wait for it to gradually get better.
That was
it seemed like it was getting better. And now I'm like, it just kind of went out of, like,
fashion, vogue,
I don't know, just out of the social conscious, like, out of the discussion. Like, and it's like, well, is it fixed or not? And like, I still feel like I get sunburnt all the time. And obviously, like, the ozone hole, there's like the ozone layer and then there's a hole in it, but then there's some there and there's not some there. Anyway, I don't know where it's at. And that's why I'm super, super excited to have Mallika and Hannah, like Hannah Montana. But you're not from Montana, right? You're from
Virginia,
which is not Montana at all.
No.
But it's in the same country-ish. Anyway, sorry, Hannah and Mallika here from the physics department. Mm-hmm. So you are both part of a massive big project in the physics department. Yep. Is that right?
That is right.
That's right. And it's a brand new project and it's an MB funded one, so it's huge and it's got like a whole team of people there.
Yes, that's true. It's made up of a lot of collaborating institutes as well. We've got an atmospheric science team that's mostly at Otago, a photonics team that's also mostly at Otago, and a space engineering team that's at Victoria University, Wellington.
Oh, right.
So those are the three
big teams.
Yep.
Okay. Wow. So, and it's a huge amount of money. Are we allowed to say how much money it is?
Sure.
How much money is it?
Yeah.
It's about 10 million for 5 years.
For 5 years, wow.
But I do always like to add the caveat that all of that money does not come to us, but goes to a lot of external contracts, like the one to University of Wellington and to Kia Aerospace, who are our industry collaborators as well.
Right, so, okay, cool. Yeah. And we kind of like to start the show just to kind of give people a feel for who you are and how you became the person, the place you are and what you're doing. And then we'll talk a little bit more about the research project and the ozone and everything at the end. If you're okay with that. I thought I'd start with you, Mallika.
Sure.
So, Mallika Suresh,
yes.
You are an optical physicist, post-doctoral researcher in the physics department here at the University of Otago in the Dodd-Walls Centre for Photonic and Quantum Technologies. I might come back to that as well. So you did a combined BSc Masters from Trivandrum?
Yep.
Trivandrum.
In South India.
In South India. and a PhD at the Max Planck Institute for the Science of Light in Erlangen, Germany.
That's correct.
And then you shifted to New Zealand, and then you joined kind of the physics department, and then you got awarded this Agnes-Blackie Research Fellowship.
Yes.
I mean, that sounds like a cool thing as well.
It was very cool.
And you're still on that, are you?
I am on the last 6 months of it, actually.
Oh, right. Because that was like 2023, and now we're in 2026.
It was a 2-year fellowship that also had an outreach component that I'm very fond of. So talking about science to people who aren't physicists themselves.
Right. So, I mean, that's, that's most likely, that's a large portion of our audience out there. And obviously neither Trudi nor I are physicists.
Obviously.
Well, you just said you did social thingies. You didn't have physics in your list of thingies that you did.
Hey, I watched the Big Bang Theory.
Are you guys Big Bang Theory fans?
Unfortunately not.
Yes, same.
Yeah, see, do you know what? Every physicist that I know, because I'm not a physicist, but I do know quite a few physicists, not a single one of them is a fan of the Big Bang
I
Theory.
can believe that.
It's a bit stereotypical, I find.
Yes,
Mind
it's a bit
you.
close to the bone, I always think when they're thinking there. But when you're like on the outside looking in and you have quite a few friends that are in that zone, a lot of it seems to...
No, don't say that because
Okay, no, it doesn't at all.
I hate
Okay.
The Office, and that's what I do. 'Cause I know I see myself. Okay. But we also have Dr. Henna with us, who isn't from Montana, so enough. So you did a BSc from the University of Virginia. What was that about?
Yes, it was just a general degree in physics. I did some particle physics research while there, so I really fell in love with research along with my studies.
In particle physics, there's a little bits that float around. Is that right?
Yes, we were looking at muons and neutrinos that come from space and developing devices that would detect and count them, essentially.
Can you give us like a 5-word explanation of what a muon and a
Neutrino?
neutrino
I would
is?
think of them like in the same groups as electrons. They're tiny particles. They're like fundamental building blocks, and they get emitted from various sources in space. And they don't really hurt us, but they're always coming through the atmosphere. I think about 100 muons pass through us every second.
So just go through us?
Yes.
And they're kind of spaced out. If there's like only 100 through us.
Yes.
So why are we interested in them?
This project was looking at seeing if any muons would convert to electrons, which is not meant to be physically possible. So it was called mu2e. And they needed to shoot a beam of muons and then count them at the other end. So we had to count all the ones coming from space so that we could rule them out and almost like exclude them from the
How do
experiment.
you count them? Like they're incredibly small, right?
Yes.
1, 2.
So we had these things called scintillators. So when the muon would pass through it, it would create a little bit of light that you could detect and count how many photons of light it generated. And then you could figure out where and when it went through the detector.
But then once it goes through, like it makes a little bit of light, doesn't
Yes.
it then disappear into the light?
It just disappears. It keeps going. But then the software can say, okay, there was a muon that passed through at this one moment, so we don't count that one. So it was like not blocking them, but just like
You want to
ruling
take them out of the equation kind of
Yes.
thing. Yeah.
Yes.
Yeah. Yeah, interesting.
Sorry, Mallika, I forgot to ask you
No, that's okay.
what your combined BSc Masters, like what the project was all about.
Yeah, so it's I did 2 years of physics, chemistry, maths, and biology because I was one of the people who didn't want to have to choose so early.
Right, yes.
And then for the remaining 3 years, I did a lot of physics. And for my 5th year, my master's project was on making small devices similar to what the work I do over here, actually.
So you actually build things.
Yeah, so we
devices.
make little optical devices out of different materials like silicon and lithium niobate, which are all just different crystals that have different interesting properties that allow us to mix different colors of light together. So some of the work that I did during my master's was related to that. And now I'm using that experience to actually make a device.
Okay, so that was your master's.
That was my master's.
And then you went on to do your PhD. And your PhD was at the Max Planck Institute,
Yes.
and that was all about light and stuff as well.
Yes, that was slightly more fundamental science where I used very short pulses of light, sent them through fibers filled with gas and understood how they interacted with the different gases.
Right.
So I gained a lot of expertise that I then used to set up a device over here at the Department of Otago. There's a femtosecond laser machining system that we use to cut different materials and make them into the shapes that we want them to be. So we can make things like discs and long rectangular waveguides, things like that, all to send light into them and get them to the places we want and get them to get those photons to do the things that we want them to do.
Crikey.
I was going to ask what a femtosecond is.
It's a very, very, very small measure of time. So a femtosecond pulse is a pulse of light that exists for 10 to the minus 15 seconds. So that's a billionth of a millionth of a second.
So how do you know it even exists?
We can measure it with
Something else that you built.
little photodetectors, yeah.
Right.
And the pulses that I work with over here, they carry a lot of power. So they're very high energy. And that's why we can use them to evaporate away material and make the different structures that we want to make.
So these
it's kind of like
structures-
cutting it.
These structures that you're making,
Yes.
how big are they?
Very small. They're about 0.5 millimeter high and about 3 millimeters wide. So they're very, very
so
small.
they're quite small, but next to a femtosecond, like that's really
Yes.
that's like really, 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 really short time.
Yes.
So that's like they're not like sort of
Now,
super tiny.
we can make very
you can
small
actually
things.
like something
but-
that's like 0.5 millimeter by 3 millimeters. You can actually see that.
Yes,
right?
you can.
But it's
Yeah.
quite a bit smaller than a button or
Yes.
a sequin. I think it's funny because sometimes people lose them if it gets dislodged and then
Yes.
it falls on the
What, the
ground.
femtoseconds? Oh, it sounds
No,
like
the-
No, the device.
sorry, not the femtoseconds. The things that you're cutting out with the laser.
the little pieces of glass and silicon that we're cutting out.
So that's what
because
these
they're
things
so
are made
small.
of.
Yeah.
And then you're shining the light through those.
we're sending light into them sometimes to make the light go around and around in them. So I make these little discs. We cut them with the femtosecond laser.
Yeah.
We just use this very high energy of light to cut away the material and then polish it. And then we can do our actual experiments with it, which is to send light through it, much lower energy light, through it and get it to circulate around in the disc.
So
That's
the
one
light
of the
just
things.
goes round and round in the disc.
Yeah,
It's like the wheels on the bus.
But how does it go round and round?
because
Like, does it hit the side and bounce
yes,
around?
Yeah.
that's exactly what it does.
So it's not really going round and round. It's going like ding, 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 and hitting the side. And
Each of those bounces are very short, so it's kind of following the
But they're still
circumference.
linear, aren't
so
they?
it's-
But
yeah.
each,
It's
like
nothing.
each one still has to be aligned. No, you can't make like
Yes.
bend in a curve.
Yes,
You just make it go in
also
like
you-
lots of little bits.
yes, but if you have a lot of little lines, they're approximately a curve.
Curve. Yeah.
Right, yeah. But it's still approximately a curve, right? I mean, it's a very small curve, but it's still approximately a curve.
Yeah.
Okay, cool. Now I feel
Right.
like I feel like I rudely interrupted you, and we have to go back to talking about Hannah.
Well,
we got sort of-
it kind of merges because you were an engineer at HP. I know, like
Yes.
it's a bit different engineering, but it's still engineering.
And it's
so-
not the source, right? It's not HP source.
No, oh yeah, it's that.
It's
You
Hewlett-
won't know what HP source is. She's introduced a variable that nobody knows about. So we're talking about Hewlett Packard here.
Yes.
Yeah.
So printers.
Yeah,
Yes.
printers.
So I was on the printer side of things.
Right. But so you did was it OCR, optical character recognition?
So I was working on what's called like vision systems engineering. So we were in the R&D side of the company, and when people are developing the little print heads that you like install into your printer, they have quite an advanced problem of looking at like tiny droplets.
Sorry, I'm just going to interrupt here.
Yeah.
What do you mean the print heads that you install in your
You
printer?
know,
Like the print
ink.
cartridges.
the cartridges.
The
yeah.
cartridges of ink.
Yeah.
Not just the ink, but the piece that like
That
actually
spits it
takes
out.
the ink and like drops a drop.
Like the piece that's attached to those like solid cartridges, not part of the printer that's already there.
Right, yes.
Yeah.
Yeah, so it's like inkjet, where you have tons of like thousands of nozzles that like right at the right time drop a certain size droplet down onto the paper
Right.
to make words or pictures.
Right.
and it's very advanced in the timing and like the amount of ink and where the ink hits because the paper's moving while you're dropping the ink. All that stuff matters, and so it's like a bit of like a fluid dynamics.
Yeah. It's actually way more like when you start to think about it, you realize how miraculous printers actually are. Because when I was probably when you started as a kid as well, printers were like dot matrix, so they were literally doing one dot. Like 9 dots for a letter, and all the letters were all square, right? Like you were obviously far too young to remember any of this. And they made this really weird noise, and the paper, in order to go through, had little cogs on the side of it, little holes, and the cogs wound it through. So everything was like way slower, and it would go. You remember dot matrix, don't you?
Hey, I even predate those. I think we're Bender machines. I think we should just move on.
Anyway, so being an HP engineer,
yes.
So you were working with colours and photons then?
Yes, and I was looking at the high-end camera system you would need to look with ultra-high resolution at those drops and then see if they were correct. And help the people designing the printhead like develop it over time. But I found it hilarious because we were so in deep at each little droplet, but I was scared to use the printer in my aisle because it usually like would the paper be jammed or you couldn't turn it on. And that's usually it's usually not the drops that are the problem with the printer.
It's the jams.
Yes.
Yeah, that's true. And whoever uses the staple function, eh?
Hey,
I know
spent a
you
lot
do.
of effort into getting that past.
Yeah.
Yeah, having bought organisational printers, But so how did you then transition from being an engineer at HP to doing a PhD at Otago Whakaihuwaka?
Whakaihuwaka.
Thank you, Whakaihuwaka.
So for a lot of my life, I've worked in outdoor education or just done things outdoors. So I was a whitewater kayaker for a long time.
Oh, Virginia would be the right place to do that. Yeah.
Yes. And so when I did research in my bachelor's degree with particle physics, it was cool. And printers were, I guess, educational. But I never felt like I had a passion for it. But I really always cared about the outdoors. And so I wanted to figure out if there was a way to like pivot my physics career into something that related to the climate. And so that's where I was looking at programs that could let me do that. And New Zealand's a really great spot for climate physics. And so I went to the atmosphere side of things. There's also ice at Otago. And you could do ocean science, like things. There's many different avenues, but the team doing atmospheric stuff was really, really good. So
that's why you're an atmospheric scientist.
Yes,
and you're an ozone expert.
And Mallika is an optical physicist.
Yes.
And so you both come together in this one big project with a whole bunch of other people who we just won't mention at the moment because they're not in the studio. But we know they exist, so we thank them for being there. But carry on with just you two guys. And you've just come back from Antarctica. That's pretty cool. Is that part of this big project?
So actually it was for a different project. So I was helping out with a team that's part of like the bigger group I'm in, looking at using radio antenna to assess the effect of space weather on the upper atmosphere. So it's not quite my area of research, but because I studied the ozone hole, it was really surreal to be there where it happens and like have a strong connection to Antarctica.
Right.
So
and of course someone was like, you were getting a trip to Antarctica, which is not that alone. So no one's going to say no, right?
Exactly.
But I mean, I suppose some people would because they don't like the cold. But if you're doing atmospheric stuff.
Research, you got to go.
Yeah. And like basically even the Big Bang guys didn't say no to going to the polar expedition, right?
I'll take your word for it.
Okay, so let's get back to the ozone. Let's go back to the ozone. Is the ozone hole still there?
Okay, so the ozone hole is still there, but there's tons of misconceptions with how it works.
So is it going
Is it
going away? Is it getting better?
It is getting better, but it'll probably still be there for at least 40 more years.
40 more years.
Yes.
So did it get better a lot at the start and then it's just slowly fixing the last bits?
It has always been really slow to recover.
Right.
So the Montreal Protocol that you guys mentioned earlier, that was really successful, and we are reducing those chemicals.
Can you just summarize the Montreal Protocol in a nutshell for those out there who don't know what it is?
So it was like a global agreement with, I think, over 150 nations to ban ozone-depleting substances that were a part of manufacturing. So like you said, refrigerants earlier, that kind of thing. And people came together. They saw that this was actually would be really catastrophic if we didn't stop emitting these. And they've been phased out now for, I think, almost 40 years.
God, that does date me, doesn't it? Eek.
And yeah, so that is working, but
Right.
the chemicals last a long time. So we've passed the peak, and so we are going down in terms
Right.
of the amount of those chemicals, but it's a very slow process. So we won't be back to where we started for at least 40 more years.
Right, but we can kind of model and it's going down and we're no longer releasing those. So we think that, 40 years in terms of climate isn't that long.
Yeah.
Do we still have effects of that hole that we can see on people and the environment?
Yes. So the hole itself doesn't directly affect New Zealand in terms of UV. So it's not ever the reason we get sunburnt in New Zealand.
So why do we get sunburn?
So, and I would say, this is the most common misconception that I've heard. I don't think I've met anyone, including myself, who didn't, grow up thinking that the hole was...
Yeah, because it coincided with the whole, sip, slop, slap
Yeah.
sunburn, and the whole idea that, Australia and New Zealand as southern hemisphere people, we're more likely to get skin cancers because there's more likely to get sunburn because the sun's harsher here because there's no ozone. So
Yeah.
all of that is just wrong.
Pretty much.
Okay,
So,
so-
we reduced our ozone a little bit, so maybe 3% less than we used to have because of the chemicals we emitted. But that's really minor. One thing is that in our summer in the southern hemisphere, we are a little bit closer to the sun than the northern hemisphere because the Earth's orbit around the sun is not circular. So we get naturally a little bit more UV light because of that.
So we're just closer to the
So
sun.
even the northern hemisphere summer, they're not as close to the sun as we are.
Right. So that's something we can't ever change.
No.
And then the other thing, hopefully, which also won't change, is that we have really clean air here.
Ah,
So when you
yes.
have aerosol pollution, it does absorb UV. So unfortunately, that means with our nice air, we do get more UV light. And more
So we don't
sunlight.
we don't want to change that, right? We
No.
would rather have clean air and a little bit more sun.
Slip, slop, slap.
Well,
Yeah.
yeah, a little bit more. Right. Okay.
Yeah. So it's important to keep wearing sunscreen,
Right.
even though the hole is recovering, because it's totally unrelated.
It's got nothing to do with it. Oh, that's interesting. I wonder if
So the ozone hole didn't have any effect on our sunburn
No.
or our skin cancers.
No. So the ozone hole is pretty much only open above Antarctica, and it's only open for 3 months every year.
Okay, so what is the effect of it?
So
Why do we care about it? If it's not about sunscreen,
yeah.
what is it about?
That's a great question. So because ozone does absorb UV, that means it heats up when it does. So when you have this almost like a circle of missing ozone over Antarctica, that's about 25 million square kilometers. That's almost like a plunger type effect. So if it's colder than it should be because there's less ozone to heat up, then the air kind of compresses and all the circulation bands across the hemisphere kind of move towards the pole. And when you have years with more ozone, now it's hotter and the air expands, and now all the circulation is pushed towards the equator. So you know how we had strong wind events in October this
Yeah.
year? So that was related to some of those disturbances that occurred over Antarctica, in relation to the ozone hole. And so the effects are usually circulation, precipitation. So you might have
So it's more
drought,
weather effects.
much
Yeah.
more. Yeah,
So the ozone hole has nothing to do with sunburn and skin cancer.
right.
It's all about the weather.
All about the weather.
And it's so the ozone is like a layer around the Earth. Mm-hmm. That's what are we talking here? It's not that thick, eh?
When you
Or is
bring it
it?
down to the surface, it's only a couple millimeters thick. If you were to take all the ozone molecules and stack them up at the surface, but it's spread out over about 10
Because there's less
kilometers.
gravity up there.
And it's less air pressure, so
Right,
the air is
yeah.
spread out. All the air has much more space between all the molecules.
Right.
So it's really sparse, but it's about 10 kilometers high, and it absorbs a lot of the UV rays.
Right.
As
So it's
light comes down.
That must be where the sunburn thing comes from, right? Because the ozone is absorbing UV rays.
Yes.
So that's why we think that it's the hole is what's causing us to get sunburn.
Right. And if we hadn't had the Montreal Protocol and we kept emitting those chemicals,
Yeah.
we would have had almost complete ozone loss globally by 2050.
Right.
And then we would have had a global ozone hole. And so that would have caused terrible sunburns for everyone, and we probably all would have gotten cancer.
So that's where the sunburn stuff
And what
came
would
from.
that have done to the weather then? Would that just drive
Oh,
the
who
weather?
knows?
Oh, I'm sure it'd be
nutty?
pretty wild, yeah.
Yeah.
I mean, it must be so unpredictable at that point.
Yeah.
Because it's so chaotic.
And most circulation things are related to temperature. So ozone's really tightly connected to that.
Okay. So at the moment, there's a small hole over the Antarctic that's only there for 3 months of the year, and it's kind of getting smaller every year when it comes back. Is that right?
At the moment, so right now there's no hole. The hole opens every August. So
right
when it starts.
now.
Yeah, now, like today.
Yeah.
But it is, every year it does get quite big. It gets as big as it always did. So some years are worse than others, but it's not, the overall size has not statistically decreased. But
the time that it's there is less?
A little bit. And I would say...
So how do we know it's getting better? If it's not got smaller?
Yeah. So I would think of it like the ozone hole is 90% natural and 10% human-emitted chemicals. But that 10% is really important. So the ozone hole generally always forms, but then we poured in chemicals that made it really deep and severe. Right. And so we can look at that piece of it, that 10% piece, and see how that's doing year to year. But then the overarching 3-month pattern has a lot of natural circulation effects, and other external things can cause it to be open longer or shorter.
So what triggers it to open?
So what is most important is that in the winter at the South Pole, it gets very dark. And because it's dark and cold there, and then kind of normal across mid-latitudes, you get this temperature gradient that causes a circulation pattern called the stratospheric polar vortex, which is kind of like the jet stream down here in the troposphere, but starting at 20 kilometers. So it's like a circle of wind that's capturing a container of air within it. And inside that circle, it gets even colder. So there's special clouds that form that are really icy. And those clouds release the chemicals. And it's this unique
event.
That doesn't happen anywhere else, really. It's you need it to be cold enough.
Why does it not happen in the Northern Hemisphere?
Okay, so it has the same setup where you get the vortex
because it's cold
forming.
And it's dark there in winter, right?
And so what you need for the ozone to actually be depleted is sunlight. That's the final ingredient. And in the Northern Hemisphere, by the time the sun is reaching where the pole is, you start to destabilize. So the destabilization comes from waves that come from the land upwards. And there's a lot,
think about more land there.
Yeah, and it's kind of irregular. But we have, in the south, we have a circular-ish piece of land with ocean around it.
Right.
So everything sets up really similarly, but then it lasts long. And that's all the natural piece of our ozone hole down here.
Okay, so it's the weird shape of Euro-Asia, everything in the Northern Hemisphere.
Yes.
That's kind of gives it this bumpy kind of, I'm not going to be doing...
Because they're all land with water in the...
Yeah, and it's
and
all
we're
uneven.
the opposite. We're all land with water around.
Yeah, so there's Antarctica and then there's this big ocean around it.
Yes.
Right, and it's just going... And then it kind of gets... pretty much like your bathtub, right?
Yes, exactly.
It sets up that...
the vortex,
vortex going, the plug hole. It's the water going down the plug hole. But in this case, it's the air thing and everything.
Exactly. So when we have a very strong, stable vortex down here... So
it's funny, isn't it? Because you usually think of things like strong and stable as being fantastically good.
Yeah.
But in this case, it's making a hole.
Yeah.
Yeah. Yeah. And so most of the time, the chemicals are going to do what they're going to do. They are depleting less ozone over time. That's
so these
proven.
are the bad chemicals, right?
Yes, the bad ones. So they work in the very early season and then they kind of stop. Right. So then the hole stays there as long as the vortex lets it.
Yeah.
And the vortex is preventing ozone from refilling the hole.
Right.
So if we get a year where that kind of breaks down and gets disturbed and ozone kind of rushes in and fills the hole early, then that's what actually caused some of the wind events in October. So that's the natural piece that will happen anyway.
Right.
And so my research has looked at the natural pieces and if they are causing the hole to remain open longer. And so those are the parts of the ozone hole that are not getting better. Right. In some ways, they can be worse, but they're not caused by the chemicals that we've reduced.
Wow. That we put there in the first place, and now we're reducing.
Yes.
Just for clarity.
Yes.
Awesome. Oh, my goodness. Okay. So you kind of – and that's kind of what you're bringing to this big MB project, right, is your knowledge about how the ozone hole and the processes around in the atmospheric process, how they kind of interact with various things.
Yes. And a lot of times talking about the ozone hole, people ask, what can I do? Right? Because we did institute the Montreal Protocol. That's working. But the hole's very much still there. And there's nothing we can do per se that's direct.
Because it's there now because the chemicals that we put there last for a long time, right?
Yeah.
But we're kind of at a point where there's less of a focus on ozone because we've solved the problem.
Yeah.
And some of the satellites that observe it are going down soon. And so
when you say going down,
oh yeah,
Yeah, what do they...
they bring them back in.
they bring them back in, so
Yes.
they lasso
How do
them.
they do that?
Is it a tractor beam like on Star Trek?
Or like gravity, they just...
Lasso, what is it? How does this process of them go? I mean, I imagine they're just crashing it
Yeah,
all into the
crash and
ocean.
I think
burn.
that is essentially so. What they don't want is leaving. They don't want to leave debris up there. So they have to have enough fuel to kind of maneuver the satellite to leave orbit and come back into Earth instead
And
of just being a
crash.
piece of trash. Yes,
So then do they go and pick it up?
I think they won't. Well, if I can find it,
They
I would
hope
guess.
they're going to burn up in the
who is
atmosphere.
they?
Yeah.
This would be NASA for this particular satellite.
Right, okay. So the satellites, they think, okay, we're going to put it up there for 20 years, let's say. Is that a reasonable amount of time?
Yes, I think this one's
Yeah.
lifetime
20.
was expected
This one
to
we're
be
talking
25.
about. We're talking about Aura, are we?
Yes.
The NASA one,
Yes.
Aura.
Yes.
Okay, so Aura's going up into space. It goes there for like 20 years, and then like maybe it'll stay an extra couple of years,
Yeah.
whatever.
Yeah.
Yeah.
And then they just go, okay, we're going to bring it in.
Yes.
So they're basically crashing it.
Yes.
So they're destroying it.
There's no use for it at this point. Like once it comes down, it's done.
Yeah,
Yeah, but like, why isn't it still able to keep going?
because it runs out of fuel, for example.
But why can't they just send up something and put more fuel in it? Is that not better than just like destroying this thing that obviously it costs millions of dollars to make, right?
Yeah.
I mean,
Like
maybe,
the Hubble, like the Hubble spacecraft, right? They famously put like glasses on it because I don't know, the lenses were all.
They went, yeah.
I don't know what was wrong with the lenses, but anyway, famously they put glasses on it. There's lots of cartoons out there of the Hubble spacecraft with glasses on, right? So, like, there's the International Space Station. Presumably, this satellite's not so far away that it's outside of reach, and they know where it is, right? That's part of being a
Yes,
satellite,
yes.
right? It's very clear where it is.
Yeah.
So why are they I mean, this is obviously not your satellite, so you're not
No.
expected to know everything yet, but I'm just like, it doesn't make
In
sense to me.
general,
Why, like,
yeah.
if it's just run out of battery, can't they just send up a new battery or
You might
put a
not
charger,
be able
hook
to
it
interface
up?
with it without it like disrupting its orbit.
Might have what, sorry?
I don't know if you can like drive up
Hop
next to
onto
it
it.
and
Yeah.
attach
Yeah.
something to it like the International Space Station.
Can't they just tractor beam it in?
I would really enjoy it if they did it because it's really a big deal that it's going down.
yeah.
I mean, I just don't understand. They were all that expensive technology that took a lot of effort to get it off the ground, right? Getting it off the ground is
Yeah.
is a difficult thing. There's endless amounts of sunlight up there, right?
But it might
Like,
be.
it's,
it
like,
might
it's
be.
like there's no clouds in space, right?
Right.
So like solar energy is pretty much there.
But is it still fit for purpose? Because if it went up 20 years ago, yeah, you'd have to do an update. And
I think that's probably key. That
Really? Has the technology moved on that
Yes,
much?
and that is essentially the idea of our program. That
Okay,
we
so-
have an idea for how to make devices that are more modern.
Can I just roll back just a little bit
Sure.
first? What is it that this satellite does?
Yeah.
And this is part of your big project, right?
Mm-hmm.
Is to basically come up with a new idea for something that will do better and more efficiently what this satellite used to do.
Mm-hmm.
So what is it that satellite does?
It essentially wants to track different atmospheric species like ozone and water vapor.
So when
and
you say
other gases.
species, you mean
I mean different chemicals in the
you
atmosphere.
don't mean species like ecologists like me.
No.
Yeah, no. So I can see him panicking from here.
We're not talking about aliens here.
No.
Okay, so what does it do again? Start again.
It's trying to track all of these different chemicals in the atmosphere. And it does this not by measuring, for example, how much sunlight gets absorbed through those chemicals, but rather just picking up the passive emission of these different chemicals.
So it's not taking a sample of the chemicals. Like it's not
No.
like a big beaker that's going around taking a sample and
No.
I had
Right?
I had a butterfly net in mind.
Yeah. Well, when you're talking about species, but then I thought, no, it must be a beaker, right? So it's not taking a sample of them
No.
like we would think of a sample.
No.
So how's it measuring them?
So the analogy that I like is, night vision cameras and goggles, which
make
you
everything
can use
that grayscale color.
Green.
You can essentially pick up the temperature of animals and people like us. So we emit very small amounts, but in the infrared domain.
Right.
So that's why these cameras have an infrared detector that can pick up the heat signatures of animals or people, things like that.
Right.
And so this satellite had a device that essentially did the same thing. It's picking up the heat signature of these gases. These gases emit very, very faint signals in the microwave domain. So
Right.
not infrared, but in the microwave domain. This just depends on the temperature of different things. And so it's a very cool instrument because it can take these measurements throughout the day and
It's not
through
really
all
cool,
seasons.
though, is it? Like, it's not
It
about
is
the
actually.
temperature of the
It
machine.
is actually.
but it's
It
not
is
about the
actually literally pretty cool as well.
Is it cold?
Yes.
Yeah.
Yes.
Okay, so why is it cold?
Because it shouldn't be measuring its own temperature, right? You're trying to pick up the temperature of something that you're looking at, so you
Right.
shouldn't be automatically picking up your own temperature. So this is the reason that these instruments are typically very big. The Aura satellite is about the size of a bus. It's massive, and that makes it
Is
expensive.
that big for a satellite?
It is reasonably big because nowadays we have way smaller satellites that are about a liter in size,
Oh, right. So
rather than
like
a bus.
milk.
Yeah,
A milk bottle.
yeah. Well, yeah,
But they're not bottles. Yeah. Never mind.
yeah.
No, it's like it's much smaller than a bus.
Yes, exactly.
So you have to make it cold. It's not just cold because space is cold.
You have to regulate the temperature a little bit. Yeah, so you can't be just at the temperature of the surroundings, if I'm not mistaken.
So how do you make a thing in space cold?
You have a big refrigerator.
What's to say?
It doesn't have CFCs in it, does
Hope
it?
not.
No, no, I don't think so.
Sorry. That was a very bad joke. Okay. So you've got this big bus
Yes.
like thing
Yes.
zooming around.
Yeah. And it's trying to, so what it does is it's measuring the amount of ozone or other gases in the atmosphere by
Right.
picking up the thermal signature.
And it was specifically put there for the ozone.
It was put there for a number of different chemicals. Ozone, water vapor, I can't remember a lot of
So
the others.
water
Maybe
vapor is about
methane as well.
climate.
Yeah, a lot of them are about climate and
Yeah, a lot
weather.
of general climate.
Yeah.
And so they're measuring, so the sort of general purpose of this satellite is kind of monitoring the ozone
yes.
layer and the ozone hole,
So
general weather events,
Yes.
pollution, climate change.
I think, so this instrument in particular was for measuring, I think there are probably other instruments on the Aura, but the microwave limb sounder, as it's called, is
Right.
picking up the microwave signals or the thermal signals from these different gases
Right.
and giving the information, the data collected to climate scientists like Hannah and other
Right.
people around the world to model the climate.
Yeah.
So that satellite's now coming in, however they managed to get it in. And then once it's in, there's nothing else there that does the same sort of thing?
No.
Right. One of the unique aspects of it is that it doesn't just get a single number for like the thickness of ozone as a whole. It looks at what we call a vertical profile. So that's like at different layers of the
So you can see
atmosphere.
the concentration all the way up.
Yes. And with ozone, that's really important because it's not uniform. It's like there's really little ozone and then like the layer.
A big
has
band
lots.
of thick, chunky jam in the middle.
Right. And then it tapers off and then there's other peaks above that. We don't care about as much usually. But it's when you have changes that occur over time, it's really important to know specifically where because those have different effects. So not only we can see that for ozone, but all the other chemicals. And a lot of times you need those other chemicals to really understand what's driving the changes in ozone.
Right.
So that's
There's
one
just some of
problem.
your kind of confounding variables that you kind of need to know about in the space to see what's happening. So what's your big thing that you're not going to send up a big bus?
No. We want to make a device that can do these measurements by taking the thermal signal, and so it's in the microwave domain, and
Yeah.
putting that information into the optical domain where detectors can be used at room temperature. So you don't need to cool something down to a very low temperature because you've taken this information and you've put it into infrared or something like that where you can just measure with a handheld detector.
So we could send a beam up. You don't have to send anything up. Like, why can't we do something like that?
Sorry, answer that question. Go.
Because you probably would need to get the beam to go in all the different places. The reason this is nice is the same reason that a thermal camera or a night vision camera is nice for if you want to see if there are wild animals around you. You don't need to be constantly sending something out and waiting to see what's reflected, but you just pick up the signal when the species, in this case animal species, comes in front of the thermal camera.
So you're going to send a tiny satellite up.
Yeah.
And so why can't we do it from here like that? Why do we send it up there?
I think this is more to be able to get the vertical profiles.
Yes, so you can't just look up. There are instruments that just look up, and they can figure out the total thickness of ozone.
Right.
But to get the profile, you have to be in the middle of it.
And ideally above it, so the satellite would be like 600 kilometers up, but what it does is it scans. So it's looking at different slices of the atmosphere.
So it's scanning down through the ozone layer.
And then you take all the data from all these different slices and you do what we call an inversion. So you can turn all that data into like a profile of the amount of ozone at different layers, which is kind of a hard mathematical process. But you can't just take one data point to get to that.
Right. So it's not like this little satellite is swimming around inside the ozone layer.
No.
It's above it and it's scanning down.
Yeah.
And when you say like you take it from the microwaves and you put it into can you just extrapolate on what that actually is?
Sure. So most of my research for the past, I can't remember how many years now, but is about mixing different colors of light to create another color of light. And that's called nonlinear optics. So if I have a laser beam that's, let's say, at the telecommunications wavelength, so in the infrared, and I mix it with a microwave signal that I want to actually pick up, I can get the signal in the infrared domain. So I get that information because I'm mixing these two colors and generating a third color. And now this third color has the information that the microwave signal had. Let's say the microwave signal had a funny shape as a function of its wavelength.
Can I just interrupt there? When you're saying colours, you're not really caring about the colours, like whether it's red or blue or green.
That is
like
what I mean.
Colours.
That is what I mean. So the different colours is just the sort of layperson way of saying the different wavelengths of the light.
Yes, because you can't actually see the microwaves,
You can't see any of these, right? You
so
can't
they're not
see
really
the
colours, they're just the wavelengths that are out there.
Yes,
right?
exactly.
So, and you're kind of mixing two colours.
Yes.
And then getting another colour,
Yes.
which is you're kind of pushing together. You've got this wavelength and then you've got another wavelength and you're adding them together.
Exactly.
And then you get a different kind of wavelength that's the sum of those two.
That's exactly right.
And if you thought of that like as if they were colours, then colours do the same thing in the visual part of that spectrum. So you've got like yellow and blue and you put them together and you'll come out with something that looks a bit greenish.
Yes, sort of. I mean, we do use nonlinear optics even for things that lay people use, like laser pointers. Green laser pointers, for example, have infrared lasers inside them that then go through a nonlinear crystal and generate the green light. So it is doing that sort of mixing of colors, but it's mixing 2 infrared or 3 infrared photons to make a single green photon. So that's the nonlinear optics part of it. So it's not exactly like mixing paint, but it's a good analogy.
Right. So
it's more like combining ingredients to come up with something different.
Yeah, we want to see the signatures of these different gases, but we want to be able to see them without having to cool down our receivers. And so if we can get those signatures in the optical domain where we have a lot of equipment, like we have photodetectors to measure infrared light because we use them in telecommunication systems. So we would be able to just use a commercially available photodetector to measure that signal if we could just get that signature into the optical domain instead of it sitting in the microwave domain. And the reason this is easier is that microwave photons have lower energy than the infrared ones. So we're just trying to get the pattern of the signature pattern of the gas that we're interested in a domain that's easier to measure.
So you're just like you've got like a pattern that's in the microwave, right?
Yeah.
And it's low energy and it's going along, bouncing up and down, a little bit different.
Yeah.
But mostly it's all still in the same range, right? It's all down there in the microwaves. And then you just add a big chunk of energy.
Yes.
And that chunk, you add it to every little bit. So some of them go up. Like
Yeah.
they all go up the
They
same
all go
amount,
up.
basically.
Yeah.
And some of them then are a little bit
Yes.
redder or a little bit orange, or a redder orange, a little bit redder orange, and you
Yeah.
look like Christmas lights
Yeah.
sort of going along, right? And then you can like go there and you kind of go, okay, well, we know that we add this much to it.
Yes.
So in order to know how much we've got, we can now
Yes.
just read it in the colour spectrum.
That's exactly right. Yeah.
And then just take away that much and we know exactly where we're at because we know how much energy we put in, so we can just take that away. So it's just basic arithmetic.
Yes.
So it's like super fancy, but just really just
I was going to
basic
say you
arithmetic.
just dumbed it down. Like, these guys' career, and you just,
my husband says I use just too much. Anyway. Yeah, no, cool.
No, I do like making it sound easy to understand. So
okay, that's
true.
cool. And then
yes.
and the different chemicals that are up there that you're calling species, but the different chemicals, right? They all have a slightly different signature, right?
Yes.
They're emitting different.
Yes.
Like different wavelengths, basically, because that's kind of the energy that they're giving off, which we give off as heat.
Yes.
And that's why you can see us in an infrared camera.
Yes.
And I'm bigger, so I give off more infrared heat.
I mean, you have a particular shape of
Yes.
in
Cool.
infrared. Yeah.
So why do you call them species then if they're not living?
yeah, don't even get started on that.
I think that might go down the route of
let's not go.
etymology of
Okay.
species.
So you've got this really cool technology, right?
Yeah.
And you've got this big grant, and you're going to put that together. And so, how does it all work together? And what are we going to learn from this in the end? And how is it going to help New Zealand? Are we going to have better weather forecasting, for instance?
That would be the hope. And I think it's not so much that we improve from today, because the satellite we've been talking about from NASA is pretty good. But we would try to get back to this point sooner than we probably would have. So at the moment, there's not really a replacement plan.
Can't they just send up another one that's the same?
We wish, yeah.
Yeah.
They don't. They would like to do kind of new things, new exciting things.
Yeah. All right. So because I mean that's kind of what I'm like. My main question is around this aura thing. Aura thing.
Yeah.
Is it that bad that it still doesn't work? They just want something new and exciting.
It costs a lot of money to put back the exact same type of technology. So
yours is going to be
wants
cheaper because it's smaller.
Because ours is smaller, it would be able to go up in one of these CubeSats, which are these 1 liter
thing, right.
things that you can combine to make 6 liters. It's still a lot cheaper than one of their bus-sized satellites. So
that does make sense.
You could put them up more cheaply and more frequently if need be.
And it could stay there
have
longer.
more of them.
Yes, you could have more of them.
Would you have more of them? Is that good? Like, do you need to have more of them?
I mean, the idea would... I think people who work in space science don't want us to put up too many unnecessary things, but if need be, they could be deorbited and another one could be put up to replace it. So the turnover rate, I think, would be shorter.
And so
therefore
will
be
you
simpler.
get to push the button that blasts it off into space?
I think in the term of this 5-year program, we won't actually be able to put anything up on a satellite because these things, getting approvals and various things to put something up into space still takes a lot of money and a lot of time.
Okay.
And our technology is still quite new. We've demonstrated it to some degree in the lab, and the next 5 years are about trying to take that device from the lab and make it into something small enough to go up in, for example, a stratospheric glider like one that Kia Aerospace makes.
Right.
So this would be an unmanned aircraft that just holds our little device and goes around in the stratosphere. So that one would be sitting in ozone. And
So that's not above the ozone
that's not
scanning
above
down.
the ozone.
That's just in the ozone.
Yes. So it would be just a proof of the device itself working. And once that's done, hopefully some space agency would be interested in actually putting it up there
You
to use.
already know the technology works, right?
Sorry?
You already know the technology, like the theory works.
Yes. We need to make the device work with the sensitivity that we're interested in.
Right.
But we do know that the technology works.
Right. So you're kind of in the sphere of making the technology work. And Hannah, you're in the sphere of interpreting what it's saying.
Yes, and also I do some modeling of the atmosphere, so I can say this is what we should be seeing. This is the wavelength you guys should target, because they can tune all the different specs of the disk they're creating to make it detect a very specific wavelength. So we need to know what wavelength ozone emits at to target that.
Right.
So that's a lot of the work I do.
Yeah.
Okay.
So
And you can do it for other things as well.
Yes.
Like other chemicals.
Yes, exactly.
So you're a physicist.
Yeah.
So you could use it for instance, for detecting methane or water vapor or anything that's it's a global warming gas.
Yes.
Right.
Well, anything that emits a temperature, I would have thought you could adapt it to measure. Yeah.
Can you adapt it to spin around planets to see if there's life on other planets?
That would be fun.
That would be cool. It would. I mean, you could use it to spin around and find if there's water and things like that. But that's very many steps from anything I'm currently doing.
Okay, but it's out there, like horizon.
Yeah.
Speaking.
Well, you got to have a goal. You got to have a goal. Like, come on.
Okay, what have we not asked you that's important that we ask you? We've covered everything.
Yeah.
I can see it, yeah. I know, so it's amazing. So, so I guess it's really, it's kind of cool, right? So we're going to be continuing to monitor the ozone layer. Do we need to keep monitoring it? If we've stopped with the CFCs and everything now?
We definitely do. And also, once the Aura satellite's gone, we will lose some of the resolution on our weather forecasts. So this is about like the stratosphere affecting the troposphere, like cascading down. Right. Because the stratosphere doesn't change very quickly, it is a really great way to add some long-term forecasting, like propagate that downwards into your weather forecasts in the troposphere.
Right.
And when that gets deleted, essentially, with the satellite coming down, we'll lose some of that ability. And I think people will probably care more at that point about sending up a new mission.
Right.
So it's about getting that back and having people understand it's important that we retain that, especially when we have extreme weather events happening.
Right.
That are hard to predict.
So this is really going to help us predict extreme weather events.
Yes.
So then we're going to be able to give out those Met Service alerts that say, hey, there's a weather warning, it's going to be really windy, don't go tramping, like maybe stay home if you don't need to drive because there's going to be.
And even on like the seasonal scale, we might be able to say this summer will be windier or something like that. So that's along with doing the modeling, a lot of our atmospheric team is looking at bringing, conducting studies to look at the effects of ozone on regional New Zealand weather, because there's a lot of research on regional Australian effects, but not so much here. So looking at what kind of predictability we can gain by incorporating ozone data.
And is that some of the weather that goes into climate change modelling?
Yes.
And so you can kind of make those predictions better, more accurate.
A lot of it is all tied to circulation, but the chemicals that make ozone worse are very separate than greenhouse gas type chemicals, and knowing what's what and what's causing different things and attributing those things is going to be even more important as the climate changes.
Right. So that's going to be really useful for New Zealand. And can we tell if we're actually at any point making the whole global climate change less of, like, if at any point the world politicians decide, because I mean that's essentially what happened with the CFCs, right? It wasn't individuals who solved the problem. It was regulations and a world agreement, and then everybody went for it, and then there was a simple answer, right? Because it was just CFCs. And they were like, okay, we don't need these. We've got another way of making refrigeration. So that's kind of why the whole refrigeration thing got solved faster and easier than climate change. But presumably what you're doing.
Yeah, I think we need to keep doing the research to be able to answer that question and keep having these satellites that are observing Earth and keep our focus on tracking what the climate is doing. And the next 10, 20 years, that'll be very important.
Because we're over that threshold now, right? So...
Yes.
Anyway. We'll leave it there for another time. Thank you very much. You've been listening to the OI podcast with Dr Barb and Trudi in conversation with Doctors Hannah Kessenick and
Mallika Suresh.
Mallika. I've spelled that wrong on my thing and now I'm just like, oh my gosh, Mallika Suresh. Anyway, thank you very much for joining the podcast. Thank you for coming along today. It's been super illuminating. I don't know about you, Trudy, but...
My head's just buzzing.
Head's buzzing? Wow. Anyway,
I want to know, does the Virginian really come from Virginia?
I think it's from the Virgin Queen, isn't it?
No, the 1960s cowboy series. Oh, the man in the black hat riding the horse. Yeah.
Completely lost me as well. If you've enjoyed this episode, we think you'll also enjoy 113 Mathematical Models with Dr. Stephen Cornell and episode 50, Greenhouse Gases and Trees with Janice Lord. Check out our past conversations. Tell someone about how much you loved the show. Do all the things. Like, subscribe, follow, review, all those things. You can help the podcast by...
sharing. Listening, talking about it.
It's all there. Thank you very much. And thank you for coming
great.
along. It's been great.
Thank you.
You've been listening to the OI podcast, the shout out for the arts, sciences and Mataranga Māori.
You can support this podcast by becoming a member of the OI. Check out the Otago Institute for Arts and Sciences on Facebook or our website.
If you'd like to listen again to this episode or others from the series, look for the OI podcast on ORFM's website, oar.org.nz.
Brought to you by the Otago Institute for Arts and Sciences, the Otago branch of the Royal Society of New Zealand.
This podcast was produced by ORFM Dunedin with support from New Zealand On the Air.